Okay, so good morning and welcome back to another session on image processing. Is the slide visible?
Yes, sir.
Okay. So in the last class, we introduced ourselves to another transform, image transform called discrete cosine transform. What we notice here is, if you carefully observe, the basis function is actually a real term. That means you will not have any imaginary term. And I also told you in the last class, if there is a real term, then the number of multiplications will be less compared to the complex uh, basis functions. So with this, actually in fact, I had given you a problem for n is equal to 2. You were actually supposed to find the discrete cosine transform matrix. Okay, so has anybody solved it? I think I had also given what would be the answer. This is the answer. So did you verify this or should I do it? Can somebody respond? Am I audible?
Yes, sir, you are audible.
Okay, so I don't- can somebody respond? Should I do this or can we go to the next one? Okay, nobody is responding, so I will probably do it. Is the OneNote screen visible?
Yes,
Okay. So let us just look at the formula once again. It is V of k equal to alpha of k summation n is equal to 0 to n minus 1 u of n cos pi 2n plus 1 k by 2n. So let me just write that first. So the transformation will be is V of k is equal to alpha of k summation n going from 0 to n minus 1 u of n cos of 2n plus 1, I hope I'm correct, 2n plus 1, yes, into pi into k divided by capital N. So this is the forward transformation equation for one dimension, of course, and alpha k is equal to 1 by root n for k is equal to 0, and it is equal to root 2 by n for other values of k. So root of 2 by n for k not equal to 0. That means k is equal to 1 to n minus 1. So with this, let us just solve the problem for n is equal to 2.
sir, we need to divide by 2n here
Where,
in VK.
oh sorry, I think this is 2n, correct? This is 2n. Okay, fine. Correct, no? That is what, okay, good observation. So n is equal to 2. When n is 2, small n will go from 0 to 2 minus 1, that is 1. K will go from 0 to 1. So this is the observation. Therefore, the formula V of k can now be written as alpha of k summation n is equal to 0 to 1 u of n cos 2n plus 1 y into k divided by 2n. This is, sorry, 2n is 2. So I can substitute the value of n. So this is 4. 2 into 2 is 4. So this is the formula. Okay, now let us substitute k equal to 0. So v of 0 is alpha of 0 summation n is equal to 0 to 1 u of n. Since k is 0, this will be cos 0, which is 1, as you know. And alpha of 0, you know, it is 1 by root n. So this will be equal to 1 by root n. N is 2 here. So since cos 0 is 1, I can write this as u of 0 plus u of 1. That is the first equation for v of 0. Now I'll put k equal to 1. Therefore, v of n is equal to alpha of k summation n is equal to 0 to 1 u of n. So here k is equal to 1. Therefore, it will be cos 2n plus 1 pi by 4. This is the formula. So if you substitute n value of n, alpha of k, okay, sorry, this is 1, k is 1. So alpha of 1, you know, it is root of 2 by n is equal to 2, so it is root 2 by 2, which is actually equal to 1 into summation. Now let me just put the values of n equal to 0. So it is u of 0. When n is 0, it is cos pi by 4 plus u of 1. When n is 1, it is cos 3 pi by 4. So am I correct?
5 pi by, oh, sorry. Yes, sir,
Correct.
3 pi by 4.
Correct. So u root 2 by 2 is 1. Therefore, you can just write it as it is. Now u of sorry, cos pi by 4 is 1 by root 2. So this is u of 0 into 1 by root 2. And what is cos 3 pi by 4? What is cos 3 pi by 4? Cos 3 pi by 4
Sir, minus pi by 1, minus 1
minus
by
1
root
by root 2. So it is minus of 1 by root 2. So if I take the common factor as 1 by root 2, it is u of 0 minus u of 1. This is the second equation. So equation 1 and equation 2. Now if you just write the matrix multiplication, so v of 0, v of 1 is equal to u of 0, u of 1. The matrix is this 1 by root 2, which is exactly what I gave you in the last class. So v is c into u, where c for this is the discrete cosine matrix for n is equal to 2. 1 by root 2, 1, 1, 1 and minus 1. Okay. So actually C is orthogonal. In the first class of image transforms, I defined orthogonality. What do we mean by orthogonal? C into C transpose has to be an identity matrix, and you can easily verify that here. I don't think I need to do it. Okay, please check. This can be verified easily. You will get an identity matrix. So C is orthogonal here. Okay. Can we say C is symmetric? Here it looks like it is symmetric, but in general, discrete cosine transform will not be symmetric. So let me just write that here. In general, DCT matrix is not symmetric. That means for other values of n, if you do it, it will not be symmetric. So I can prove it with the next example. Next example, I'll do only a part of it. The rest I expect you to do it. So let us try for n is equal to 4. And normally uh, this is what is expected up to n equal to 4. Okay. Again, the equations are same. So here small n will go from 0 to 3. K will go from 0 to 3. Okay, so now let us write the formula. V of k is equal to alpha of k summation n is equal to 0 to 3 u of n cos 2n plus 1 pi into k divided by 2n. N is 4, so it is 8. This is the formula. As usual, we have to write equation for all the values of k going from 0 to 3. So let us do it for 0. So for 0, it is alpha of 0 summation n is equal to 0 to 3 u of n. When k is 0, it is cos 0. Cos 0 is 1. So this is cos 0, which is equal to 1, of course. Alpha of 0, as you have already seen, alpha of 0 has to be 1 by root n. And here n is equal to 4. So it is 1 by root 4. 1 by root 4. So summation n is equal to 0 to 3. So it is u of 0 plus u of 1 plus u of 2 plus u of 3. 1 by root n is half. Therefore, I can write it as half into u of 0 plus u of 1. This is the first equation. Okay, similarly you have to do it for the rest. Okay, probably I'll write it for v of 1. The rest I want you to do it, but I'll give you the final matrix. So it is equal to alpha of 1 summation n is equal to 0 to 3 u of n cos 2n plus 1 into pi k divided by 8. This is the formula. K is equal to 1, so I can just remove this. K is 1 in this case. Okay, so now I have to substitute the value of n, and alpha of 1 is root 2 by n. So it is uh, root of 2 by n, and root of 2 by n is 4, so it is root of 2 by 4. Okay, into, let us put n equal to 0. So n is 0, it is cos pi by 8 plus u of 1 into cos 3 pi by 8 plus u of 2 into cos 5 pi by 8 plus u of 3 into cos 7 pi by 8. Okay, I hope the steps are clear to you. And root 2 by 4 is actually 1 by root 2. And if you calculate cos pi by 2, cos 3 pi by 2, cos 5 pi by 2 and cos 7 pi by 2, this equation will be like this. I'll give you the final answer. 0.6532 into u of 0 plus 0.2706 into u of 1 minus 0.2706 into u of 2 minus 0.6532 into u of 3. This you can verify it later. Okay, so like this you will get second equation, and similarly please write the equation for v of 3, v of 2 and v of 3. And if you represent it in the form of a matrix, it would be like this. So the discrete cosine matrix for c is equal to, sorry, for n equal to 4 is the following: 0.5, 0.5, 0.5, 0.5. That I think we have already verified here. So it is 1 by 2 into all these things, so 1 by 2 is 0.5. The second one, I think we have done it, 0.6532, 0.2706 minus 0.2706 minus 0.6532. Third row, if you complete it, this is what you will get. Please verify it later. You will get this. When I put k is equal to 2, when I put k is equal to 3, I'll get this 0.2706 minus 0.6532, 0.6532 minus 0.2706. Okay, so this will be the um, discrete cosine transform matrix for n is equal to 4. This is for n is equal to 4. What you have to actually do is next they may ask you to show that this is the homework that you have to do. You will definitely get the answer. I'll show it by using MATLAB now. So show that C into C transpose is identity matrix. Okay, which means C is orthogonal. Now you can observe carefully, this is not a symmetric matrix. Transpose is not itself. Please observe that. This is why I told you I wrote this sentence. In general, DCT matrix is not symmetric. Only in the case of n is equal to 2, it is symmetric. But for n greater than 2, it will not be symmetric. Okay. So this is how I can get the uh, discrete cosine transform matrix for any given n. Okay. Normally, manually to calculate, usually we will expect you to calculate for n equal to 2 and 4. Beyond that, it is very lengthy, but so for which you can use MATLAB to just verify. So let me just show you that. Now this is actually the command for finding DCT matrix. Okay, A is equal to DCT of 4. Let me just run this and show it on the command window. Observe, this is what I gave you, 0.5, 0.5, 0.5, 0.5. Is the MATLAB window visible?
Yes, sir, it's visible.
Okay, okay.
Yes, sir.
Yeah, 0.6533, 0.2706 minus 0.2. So you can observe this is the DCT matrix for here. You don't need to do any scaling here as we did in DFT. Directly this is a command DCT MTX of 4. So if you give DCT MTX of say 2, you will get it for 2 by 2 matrix. So this is how you can use MATLAB to generate. Okay, and to show whether this is orthogonal or not, I just run the next part of the code. Okay, so yeah, I think I'll run this complete thing. So what I'm doing, if you carefully observe, I am generating a DCT matrix, taking the transpose of it, I am multiplying it. I should get an identity matrix. Let us verify that. Okay, so A is the DCT matrix for n equal to 4, B is A transpose. So you can observe that it is not symmetric. Okay, and this is A into B. So you can observe it is an identity matrix. All other values are 0, only the diagonal elements are 1. So that is exactly what you would be asked in the exams to start with. That means find the DCT matrix for n equal to 4 or n equal to 2 and show that it is orthogonal. Showing it as orthogonal means C into C transpose should be equal to identity. Now how do we use this uh, matrix for 2 dimension? Same principle. Now observe, this is for a 2-dimensional DCT. That means this is for an image. And the assumption is it is a square image, n cross n. And the formula for forward transformation is this. Okay, there is a constant A which can be calculated by this formula, alpha of k into alpha of l. The summation is from 0 to n minus 1. U of mn is your image in the spatial domain, and this is the basis image. Cos of pi 2n plus 1 k by 2n, cos of pi 2n plus 1 l by 2n. Here k and l are the frequency domain, the transform domain variables. M and n is the spatial domain variables. So you can already observe that this is appearing in separable form only, because it is cos of value with respect to k, cos of value with respect to s. So you are already writing the basis function as a separable function. Okay, so since it is separable, if you, I hope you remember we had discussed this, maybe I can show that. Okay, when I use separability, I can write the forward transformation by using matrix equation like this, where the matrix A is actually one dimensional matrix. So here again same thing. Since I already know how to write one dimensional discrete cosine transform matrix, I can use that. So C into U into C transpose. Now please be very careful here. In DFT, the transpose was itself because it was a symmetric okay, matrix, but here you should not forget this transpose operation. So I can use this formula to find the forward DCT of a given image. V is equal to C into U into C transpose, where C is a one dimensional discrete cosine transform matrix, which is definitely orthogonal, which we have verified. Similarly, 2D IDCT, inverse discrete cosine transform, can be represented. So the only change is U of Mn will come here, V of KL we go here, and the summation is k is equal to 0 to n minus 1, L is equal to 0 to n minus 1, and this orthogonal function doesn't change. Carefully observe, there is no change at all, same orthogonal basis function. Okay, so which can be written in the form of equation C transpose V into C. So I can find the forward transform using this equation. I can find the inverse two-dimensional DCT transform using this equation. So the next part of the problem would be, after finding the transformation matrix, one-dimensional transformation matrix for n is equal to 4, you may be asked to find the 2D DCT of a given image. Okay, so I think you know what has to be done. C into U into C transpose. So since it is a lengthy procedure, I will not solve it now, but I will show you the MATLAB simulation. But you should know how to multiply the matrices. I think it's not a difficult thing. So let me just go to the equation. I just want to find the 2D DCT of 1, 2, 3, 4, 5, this matrix. Okay. So what I want to show you here is, if I use the matrix multiplication equation, I'll get the forward transform. If I directly use this equation, that means directly substituting the values of U of Mn for each value of M and N, and calculating this, multiplying it with the constant, finding V of KL, I have to get the same answer. Okay, let me demonstrate that. That is why I am using another command here. DCT2 is the MATLAB command to find the two-dimensional DCT of a given image. Okay, I hope the point is clear to you. So let me run this. Both of them should give me the same answer. So I'll evaluate it. I'll go to the result. So this is the image 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's a 4 cross 4 image. So which means I need to find 4 okay, DCT matrix for n equal to 4, for which I am using this command, A is equal to DCT matrix 4. So I will use V is equal to A into U into A transpose, this equation, C into U into C transpose. So what is it yielded? 34 minus 4.4609 minus point. So this is the two-dimensional DCT of image U. Okay. Now I also said I can use DCT2 command to find it directly. That is what has yielded this. Compare them, both of them are same. Okay. Uh, is it clear what I have done? Can somebody
Yes,
respond?
sir.
Okay, so what I am avoiding here is this matrix multiplication that I have done by using MATLAB. You have to do it manually during test or exams. Definitely we will not go beyond dimension n is equal to 4. So this step I want you to do it and verify that you will get this answer. Okay, so this part I am avoiding in the class because I have to write so many matrices. I think matrix multiplication is not a difficult thing, all of you can manage. So in exams normally this is how the question will be given. Find the DCT matrix for n is equal to 4, show that it is orthogonal, find the DCT of a given image. So they will give you an image, you have to use matrix multiplication and do it. Okay, and cross verification is directly apply it to this formula and do it. That is a cross verification. Okay, so this is how we can find DCT of a 2D DCT of a given image, and DCT has got a very good advantage. I think all of you have experienced the advantage of DCT in terms of the JPEG images that you are reading. Okay, that means DCT is used for image compression. Okay, so these are some of the properties of DCT. First one, it is real. You saw that. Okay, the entries here, all of them are real. There is no imaginary term in the values. So that is the first property. The meaning of real means conjugate is itself. Okay, and the second property is it is orthogonal. Orthogonal means C inverse is same as C transpose. That means when I apply C into C transpose, I will get an identity. So this is the meaning of orthogonality. But you can observe here it is not symmetric. So DCT matrix is not symmetric. Please remember that. It is not a symmetric image. Symmetric matrix. Next thing is very important. DCT has excellent energy compaction for highly correlated data. Remember, I think during the properties of image transforms, I mentioned about this. Remember, this is what meant by energy compaction. That means it is the ability of a transform to pack a large fraction of the average energy of the image into a relatively few transform coefficient. That means when I take the image from spatial domain to the transform domain, I need very less number of coefficients to represent the data. I can demonstrate it now. Let me go to MATLAB. Okay, what I am doing here is I am just reading an image, of course showing it. I am converting it into gray because I want to work on gray image. Then I am showing that I am taking DCT of the image. I had already told you what is the command for that. Then I am just showing the image, that means the DCT of the image as an image. Okay, let us just run this. Okay, so I'll go one by one and explain what it is. This is the original image. Okay, I think all of you have seen this image during the class. This is a color child image, and this is the gray level version of that. So I have converted RGB to gray. Is the image visible?
Yes, sir.
Okay, fine.
Yes, sir.
Okay.
Yes, sir. It's visible.
And this is the DCT of the image. Okay, let me probably, okay. Now what do you notice here? Can somebody comment? What is it you are noticing? This is the DCT of an image shown as a matrix. Shown as an image. I am just displaying it as an image. What is it you are noticing? Any observation that you see in this matrix? In this image? No observation. At least I will just mark or show my mouse here. Observe what you see here and what you see in this portion. Any comment? Quick comment? Please
Sir,
try.
in the right downmost part, it is smooth. But
Okay, instead of smooth, the term that I use, you are almost right. This is black, right? Most of it is
yes,
black,
sir.
correct? So I have some white values here. Okay.
White pixels. Sir.
So when I show something as an image, white means it is the highest value. Black means it is almost close to zero. I think this concept you already know. 0 appears black and 255 appears white. So what you notice here is even though the DCT is of this dimension, in fact it will be of the same dimension as that of the image, but the coefficients are in fact uh, higher here, whereas most of these coefficients are 0, which means that I don't need all these coefficients to represent the data. If I just use only these coefficients, some coefficients here, I can I can represent the data. That means an image of this dimension, okay, an image of this time, of course, let me not go to the color one, the gray one. So this is the dimension. I can represent this dimension data by using only few coefficients here, because the rest of the values are 0. In fact, you should have noticed that when I ran this program also, let me just run that again. Just a 4x4 image. When I run it, what you noticed here is, just observe, this is 34 maximum. These are some negative values, and all these values are zeros. Notice all these values are zeros. So only few coefficients exist. Only few coefficients exist. The remaining portion is 0. So if I just only use these few coefficients and reconstruct the data, I will get back almost close to this. In fact, I will demonstrate it by using a simulation. So let me just run this completely. Okay, and I'll explain it later. Now observe what is that I have done here. After taking the DCT of the given matrix, in this case what I have done is, I have first generated a zero matrix of the size of the image, and I am just copying the first 20 by 20 coefficients into Z, and remaining things are 0, and I am just showing it as an image. In the next case, the first 50 by 50 coefficients are copied, the remaining are made equal to 0, and I am doing inverse DCT. Here 100 to 100, here 1 to 150, and 1 to 250. Now observe in the images. So this is the original image. This is, of course, I think this is already seen. Okay. Yeah, I think I should explain this also. I'll come back to that later. So this is by taking the first 20 by 20 coefficients. Okay, what you should notice is at least some portion of the image is visible. You can say that it looks like a child image. Then I think this is yeah, this is when I increase the coefficients. This is when I further increase the coefficients. Okay, so observe here, I am only using, let me just close all these things. So I am only using 1 to 150 and 1 to 250. The remaining values are 0. I have almost reconstructed back my image. Of course, this is not a good way of doing thresholding. There is a very intelligent way of doing thresholding which is beyond the scope of this syllabus. So what you should understand is, this is very important to me. In fact, this is what is important to me. When I take DCT of a given image, majority of the energy of the signal gets concentrated in lesser number of coefficients. The remaining coefficients values are very minimal. So I can represent a big data by using less number of coefficients. This is a concept of compression, and this is one is being used in your JPEG images. DCT is used in JPEG. Okay. Yeah, I think one more thing. This is a three-dimensional view of the coefficient, just to show you that they are, in fact, minimal. So let me just rotate it. Mhm. So observe here. Only I have few coefficients here in the corner here. All other values are 0. Observe. Only few coefficients are there. Do you able to notice it? Okay. So only this peak means it is the highest coefficient. All other values are 0. That's exactly what is shown here. Only these values are higher, all other values are 0. So this is the second property. That means DCT has got excellent energy compaction for in fact correlated data. The third one is DCT separable, which you have already seen here. In fact, you are representing it as one dimensional into one dimensional. That means I can do this, and separability in fact helps in fact calculating the values fast. And So DCT has got some properties for which you can implement it fast, just like FFT algorithm. Here also you have fast way of implementing DCT, and actually it okay, for n element vector you need actually n log n base 2 operations. Okay, similar to what you have studied in DSP. Okay, so this is about DCT. If there is any specific question, ask me. Otherwise, I can go to the next one, which is Hadamard. Any question?
No, sir.
Okay. Yeah. See, when I showed when I actually motivated you from DFT to DCT, what I told is DFT matrix is complex. So whenever I had to do complex multiplications, I need many real multiplications. That's what I demonstrated it to you also. Hopefully you remember that. Yeah, here when I multiply two complex numbers, you will have four real multiplications. So if I have a real matrix, I can avoid it. Okay. So that's how we got DCT matrix. This is real. But here again, you can observe that the coefficients are in fact 0.6532 point. That means the values are in fact, so when I are multiplying, you have to multiply them, zero point 0.5 into something, 0.6532 into something. So I need to multiply with these constants. Now the next question that we are asking is, what if this matrix will have only 1 or 0 in the entries? Okay, so that is what is answered in the next matrix. So I repeat, your elements of the basis vectors, if they take only binary values, you have an advantage, because if I have 1, I have to just copy the value. If I have 0, I'll write the value, because multiplication with 1 and 0 is easy for you. I think you can understand. So if the entries in your matrix is 1 and 0, then I'll have an advantage. That means the computation is still fast. So it is very well suited for digital signal processing. Okay, so for processing a huge data, if the matrix has got only binary values like 0 and 1, I'll have an advantage. So one such example matrix which will have only binary values in the entry is Hadamard transform. Hadamard transform, the name Hadamard transform. Okay, and the equation is similar. There is nothing. So as you saw, in every case I'll have a summation, I'll have the signal in the time domain, and I'll have some basis function. So here this is the summation. Okay, this is some constant coefficient. This is your signal in the time domain. This is your basis function, minus 1 to the power of b of kn. What is b of kn? B of kn is summation I going from 0 to r minus 1 ki ni, and ki ni are actually 0 and 1 obtained by representing k and n using binary. Say for example, if k is equal to 2, I'll represent it as binary 1 0. If k is equal to 3, I'll represent it as 1 1. So that means your k and n, that is these values ki and ni, will always be 0 or 1. So when I multiply them and add them, this b of kn will be either odd or even. Obviously, for example, if both of them are 1 and 1, then it is 1 into 1, so the value sum will be equal to 1. So either I'll get an odd value here or an even value. So minus 1 to the power of even value means I'll get positive. Minus 1 to the power of odd value means I'll get negative. So what you notice here is, except this constant, I will get something like u of n into minus 1 depending on the value of kn. So it will be something like u of 0 plus u of 1 minus u of 2 minus u of 3. So which means I'll have only plus 1 or minus 1 or 0 as the entries. Okay, anyway, we'll take an example and do it. So this is how we can represent it. In fact, there is an easy way of doing it directly, but to start with, we have to start with n equal to 2. So let me just do that. I will probably go to another page. Okay, so what we will do is we will just write Hadamard transformation matrix for n is equal to 2. We will do it for this. The rest is easy. We will use a different method. Okay, so go back to the formula. This is the formula. V of k is 1 by root n summation n is equal. So V of k is 1 by root n summation n is equal to 0 to n minus 1 u of n minus 1 to the power of b of kn, where b of kn is summation I is equal to 0 to some r minus 1 ki ni, which are the digits used for representation. That's what it means, ki ni. Okay, so let us take, so in this case n is equal to 2. So the formula will be V of k is equal to 1 by root 2 summation n is equal to 0 to 1 u of n into minus 1 to the power of b of kn. Let me write both the equations. K will go from 0 to 1, so V of 0 will be equal to 1 by root 2 into u of 0 minus 1 to the power of b of 0 comma 0, because n is equal to 0, plus u of 1 into minus 1 to the power of b of 0 comma 1. I will also write the next equation, then we will try to calculate these values. 1 by root 2 into u of 0 minus 1 to the power of b of 1 comma 0 plus u of 1 into minus 1 to the power of b of 1 comma 1. Now I need to find these values, b of 0 0, b of 0 1. Definitely it will be either even or odd. Okay, so let us just try to find b of 0 comma 0. What is the formula? It is summation I is equal to 0 to r minus 1 ki ni. So your k is taking only value 0 and 1. N is also taking value only 0 and 1. So to represent 0 and 1, you need only one digit. You know that. That means 0 is represented as 0, 1 is represented as 1. You need only one bit. So obviously, the summation will be from I is equal to 0 to 0. So it will be k0 n0. That's all. So you know the 0th digit is 0 for, okay. So for this is k, this is n. The 0th digit is 0 for this, 0 for this. So it is 0 into 0. So your b of 0 0 will be 1. Sorry, 0. For 0 and 1, it will be k naught n1. Sorry, k naught n naught. So 0th digit is 0 for this. And 0th digit for this is 1. So it is 0 into 1. 0 into 1 is 0. B of 1 comma 0, same thing. For this it is 1. For this it is 0. So it is 0. And lastly B of 1 comma 1, it is 1 into 1, which is equal to 1. So these are the values. So if you substitute these values in the equation, V of 0 will be equal to minus 1 to the power of 0 0. So anything raised to the power of 0 is 1. So the first equation will be 1 by root 2 into u of 0 plus minus 1 to the power of 0 is u of 1. The second equation is v of 2 is equal to, sorry, v of 1 is equal to 1 by root. Can somebody tell me what is this? Quick.
U of 0 minus U of 1.
Very good. U of 0 minus u of 1. So this can be represented as usual in the form of a matrix. So this is v of 0, v of 1. So you know that 1 by root 2 can be taken as common factor. So 1, 1, 1 and minus 1 into u of 0, u of 1. So remember, This is your Hadamard matrix. So V is equal to Hadamard matrix. Maybe I'll just write it. Okay, H into U. So H Hadamard matrix for n is equal to 2 is 1 by root 2, 1, 1, 1 minus 1. So as you saw, except this, don't forget, don't worry about this, because this is one single constant, you can multiply it in the end. You can observe that all values are either plus 1 or minus 1. So you will not have any um, integer values other than 1. That means it is binary. So this is for n is equal to 2. Now for n is equal to 4, we will not use this method. Don't worry. That's why I told you this is only for n is equal to 2. Okay. For n is equal to 4, we'll use a different technique. So let me go back to that. Okay. Now this is how we represent Hadamard matrix for small n equal to capital N equal to 2 or small n is equal to 1. See, H1 means, I think you should know that notation, because sometimes it would be confusing. Okay. Uh, Either you can represent it as H small n, or you will represent it as H capital N. Okay. So capital N, if it is 2, actually it is written as 2 to the power of n, which means for this case small n is equal to 1. So if I write H1, it means that small n is equal to 1, which means that capital N is equal to 2. That is how you have to understand. Be very careful. Okay. So here this is for n is equal to 2. Okay. N is equal, small capital N is equal to 2 or small n is equal to 1. That is the mean. This is the starting point. Now to find, for example, if I want H4, okay, let me just go here. Suppose if somebody asks me, I want for n is equal to say 4. Okay. Now you know this can be written as 2 to the power of 2, which means small n is equal to 2. So I am interested in finding H2. It is easy in general. Let me go to the, in general, any Hadamard transform for any n can be calculated as h of n minus 1. This is a product. This is called Kronecker product. Let me write that. Hn can be determined by finding Kronecker product of Hn minus 1 into H1. This is called Kronecker product. This is a peculiar product of two matrices. Okay. I will show you what is that Kronecker product. Let me just probably go to, yeah. So this is from internet. Okay, I've just opened it in internet. Assume that I have two matrices and I want to find the Kronecker product of these two. Carefully observe what I am doing. The first element into the matrix. Observe, first element into the matrix, second element into the matrix. Okay, third element into the matrix, fourth element into the matrix. This is how you find it. So when I multiply this, I'll get some values. So Kronecker product of two by 2 matrices, I am getting a 4 by 4 matrix. Okay. It is not the direct matrix multiplication. I am taking each element and multiplying all the elements of this and writing it here. Each element. Okay. So is the Kronecker product understood? How it can be done? Take the first element, multiply all the elements of the matrix, write it here. Take the second element, multiply all the matrix elements, write it here. So let me just go back now. Now I want for say H2. According to the formula, it is H1 Kronecker H1, and H1 is 1 by root 2, 1, 1, 1 and minus 1. Kronecker 1 by root 2, 1, 1, 1 minus 1. So if you do this, I think 1 by root 2, 1 by root 2 can be taken outside. So I'll write it as 1 by root 4. Carefully observe the first element into the matrix. So 1 into this, 1 into 1, 1 minus 1. Second one, again 1, 1, 1 minus 1. Third one, 1, 1, 1 minus 1. What will be the fourth one? What are these values?
minus
Minus 1,
1, 1,
minus 1.
1 minus
Minus 1, minus 1, minus 1, plus 1,
Plus
correct?
1.
Correct now? Okay, so this is the Hadamard matrix for capital N equal to 4 or small n equal to 2. Okay, that is how you can write the Hadamard matrix for, I don't have it for that. So this is for n is equal to 4. Similarly, you have to do it for n is equal to 8. Normally we will not go beyond n is equal to 8, and you know this is equal to 2 cube, therefore it is small n is 3, so it is h3. This is equal to, as you know, it is h2 Kronecker h1. So you have h2, you have h1. Okay, h1 is here. Find the Kronecker product. Okay, of course this is also same as h1 Kronecker h2. It is commutative, so you can either do this way or that way. Okay, so what you need to do is this matrix. So I'll write the step 1 by root 2. I'll use this equation 1, 1, 1 and minus 1 Kronecker 1 by root 4 1, 1, 1, 1, 1, 1 minus 1 1, 1, 1 minus 1 minus 1 minus 1 minus 1 1. Okay, so I have to take the first one, multiply with this, so it will be something like this. It will be 1 over root 8 into, I'll write only the first portion, the rest you can do it. So this will be 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1 minus 1 minus 1 minus 1 minus 1 1. So similarly this, in fact it is a copy of this. This also it is a copy of this, only here it is a negative of this. Okay, I hope the steps are clear to you. So I'll show you the final answer here. This would be the matrix. Okay, so what you should notice is, except this constant which can be taken up in the end, only one multiplication with this. See the entries here, they are 1 and minus 1. So multiplying with 1 means there is no, in fact you don't have to spend any computational uh, time on that. Multiplying with minus 1 means you have to just negate the value. So there is actually no multiplication at all, you will have only addition here or subtraction. So thereby you can reduce the computation if I go for a Hadamard transform. Okay, so with this let us I think stop now. I'll just share the attendance link quickly. All of you give the attendance.